Hello, GCC students. Welcome to a new chapter. We're now on chapter 10. Chapter 10 is going to be a mathematical chapter, so get your calculators ready. We will also want to have our periodic tables uh, available to look at as well. So, calculators and periodic tables out. We're going to talk about the mole in this chapter. So, first, I need to tell you what the mole is before we get to those calculations. So, to explain what the mole is, I need to tell you about Avogadro. So, Avogadro is this scientist here who came up with a number. Let me explain to you why this number is important. I'm going to do that with an analogy. Eggs. When you go to the store, you don't buy one egg at a time. That would be hard to wrap it up, and then you'd have to buy a bunch of them probably. So, it's convenient to package them in a dozen or 12 eggs. That's just convenient. So we put eggs in cartons for 12 of them, and we call that a dozen. So if a foreign exchange student asked you, what does a dozen mean? You'd probably say 12. And they'd say, 12 what? And you would say, no, just 12. 12 things, 12 items. A dozen is just the number 12. And it can be applied to anything. You can have a dozen cars. You can have a dozen eggs, a dozen donuts, a dozen cans of beer in a 12 pack. You can have a dozen buttons. You can have a dozen pens. You can have a dozen people. It's just the number 12. And it's convenient for eggs. Well, now we want something convenient for atoms, except atoms are amazingly tiny. So 12 just won't work. We can't count out 12 atoms. So our numbers can be much, much, much bigger than that. In fact, it's going to be millions of gillions of billions of gillions, gazillions. It's going to be a huge number. So it was Avogadro that came up with this convenient number for atoms. And the number is 6.02 times 10 to the 23rd. That's like 600,000, thousand, million, 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 gazillion, 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 etc. atoms. It's a lot. And he called that a mole. MOLE. One mole is 6.02 times 10 to the 23rd. Just like a dozen is 12, a mole is 6.02 times 10 to the 23rd. So a mole is just a really big number. It's Avogadro's number, symbolized there with a capital N and a little subscript A, number for Avogadro. So Avogadro's number is just a super large number, and it's convenient for atoms. So, the mole. Why haven't you heard of the mole before? Well, if we had a mole of softballs, it would fill up the planet Earth. So, that's a lot. We don't have that many softballs on planet Earth, or we'd be buried in softballs. So, you haven't heard of the mole before because a mole of most things we could see would be more than we have on the entire planet. But atoms are so amazingly tiny that one mole of atoms will fit in your hand. It's a handful. So, a mole of atoms can fit in your hand. Now, if it's a little atom, it's a little handful. If it's a big atom, it's a bigger handful. But a mole of atoms can fit in your hand. See, it's convenient, right? It's convenient. All right. Now, the mass of a mole of atoms is actually in your periodic table. It's the mass, the atomic mass that we talked about before in grams. But now we're going to have a unit for that. It's going to be grams per mole. For example, find carbon in your periodic table. Okay, find carbon. And we see the mass number is 12.01. 12.01 grams per 1 mole. So a handful of Avogadro's number of atoms would weigh 12.01 grams. That's 1 mole. Find sodium. Find sodium in your table. There it is. And you see the mass is 22.99. So that means 1 mole of sodium atoms in your hand would weigh 22.99 grams. It's 6.02 times 10 to the 23rd atoms, and it would weigh 22.99 grams. So that's why Avogadro's number works out so amazingly well. All these masses in the table are the grams in 1 mole, grams per 1 mole. So that is the molar mass number now in our periodic table. From now on, that number will be grams per mole. Here's some photos of 6.02 times 10 to the 23rd atoms or molecules, in this case, of some ionic compounds. So we see salt. Salt is 58.5 grams for 1 mole. We see iron 3 chloride. We see copper 2 sulfate. We see potassium iodide, some potassium manganate, and some cobalt nitrate. So all of these would fit in your hand. Again, it's 6.02 times 10 to the 23rd units of these ionic compounds. So those are some pictures of a mole. Mole examples. Again, a mole is just 6.02 times 10 to the 23rd of these things, items. These items can be anything, but again, talking about cars or people or baseballs, it's just too many. We don't have that many of those things, 6.02 times 10 to the 23rd of them on planet Earth. So we only really use a mole when we're talking about the items that are atoms, molecules, ions, which are just atoms with a charge. And in the case of ionic compounds, we call them formula units, like NaCl. That's a unit, an ionic unit. So if we have 6.02 times 10 to the 23rd units of NaCl, we would have 1 mole of salt. So 1 mole is 6.02 times 10 to the 23rd atoms or molecules or ions or formula units. That's usually what we use them for. Great. Okay, as we already mentioned, in the periodic table, those masses now are going to be grams per 1 mole. We call this the molar mass, the mass in a mole, molar mass. So the mass that belongs to 1 mole. So let's get our periodic table out. How many grams are in a mole of boron? What's the symbol for boron? Do you remember? Yeah, B. Find B. There it is. And how many grams are in a mole? 10.81. Good job. Okay, how many grams are in a mole of gold? What is gold's symbol? Do you remember? You're correct if you said AU. Find AU. There it is. So 1 mole of gold weighs 196.97 grams. Last one, zinc. What's the symbol for zinc? Yeah, you're correct if you said ZN. So ZN, find it in the table. There it is. So zinc is 65.38 grams for 1 mole. Good job. And remember, a mole is just 6.02 times 10 to the 23rd atoms of these elements. And again, it'll fit in your hand. It's about a handful. 1 mole means MOL means a mole, MOLE, not a molecule. So MOL is the abbreviation for mole, MOLE. It is not an abbreviation for molecule, by the way. Okay, MOL stands for MOLE. All right. Okay, let's have you try these. What is the molar mass of silver and potassium? Hit pause. Look these up on your own. Silver and potassium. All right, I hope you remembered that silver is Ag and potassium is K. Hopefully you found those in the periodic table. And silver is 107.87 grams per mole, not just grams, but grams per mole. That's the proper unit. That's important. Grams per mole. Because it's not just any old grams, it's the grams in 1 mole. Potassium is 39.10 grams per mole. So those are for atoms. What do you think we do to get the molar mass of a compound? Like if we wanted the molar mass of salt, NaCl, how would we get that? Think. Oh, well, we would just add up the Na's mass and the Cl's mass and put them together, right? Just add the two atoms up together. That is correct if you thought of that. You just add up the molar masses for all the atoms in the compound. Okay, what's the molar mass for N2H4? Here's where you need your calculator. Grab that calculator. N2H4. So we need to add up how many masses of nitrogen N? 2, right? So that would be 14.01 times 2 equals 28.02. Plus, we need 4 hydrogens. And hydrogens are 1.01. So 4 of them would be 4.04. So plus 4.04 equals, what'd you get? If you got 32.06 grams per mole, you're correct. Remember, it's not grams, it's grams per mole, because we're talking about 1 mole, or 6.02 times 10 to the 23rd molecules of N2H4. Okay, so we're specifically talking about 6.02 times 10 to the 23rd molecules of N2H4 and how much that weighs. And it's 32.06 grams per mole. Okay, so that is molar mass. Hope you're doing okay so far. All right, one more slide and we'll take a break. Let's calculate the molar mass of barium hydroxide. Barium hydroxide. Well, here we go with names. You've got to know the formula for barium hydroxide. I want you to hit pause, figure out what barium hydroxide is, check your charges, and then add up the mass for every atom. Hit pause. Okay, barium. What's the symbol for barium? Ba. Hydroxide. Ooh, that's one of our polyatomic ions. It's here in this box on our table. Polyatomic ions. It's OH minus. So we've got to put barium and OH minus together. Now, barium is in the second column, right? Here's barium. Barium's in the second column. So it's a +2 charge, whereas hydroxide is just -1. So we have the 2 to 1 combination, 2 to 1. So do we need 2 bariums? No, we need 2 hydroxides. So the formula is Ba in parentheses OH with a 2. We need 2 hydroxides to make -2 to go with the +2 of barium. This is so important. You've got to be able to put together these ionic formulas. Check your charges. Barium hydroxide, Ba +2 and 2 OHs to make -1, -1, or -2. It adds up to 0, so that's the formula. Ba in parentheses OH with the subscript 2. All right, now we just need to add up the mass. How many bariums do we need? Just 1. How many oxygens do we need? 2. How many hydrogens do we need? 2. So we need to add up those atoms. So hit pause if you haven't done this already. Hit pause and add it up. Okay, so barium is 137.33. Then we have 2 oxygens at 16.00. Don't forget the 00. Those are sig figs. So you need to remember that those count as 2 decimal places when we're adding stuff up. And then 2 hydrogens at 1.01 each. You add that all together, you get 171.35 grams in that mole. Again, we are adding up 6.02 times 10 to the 23rd units of barium hydroxide, and it's 171.35 grams for that 1 mole. That's a good time for a break. Got a good start in chapter 10. Catch you in the next video, GCC. Bye-bye.